In first law actually deals with interconversion of different forms of energy. Interconversion of different forms of energy. And it tells if one form of energy disappears, then equivalent form of any other form of energy should appear somewhere else. That is conservation of energy. And if you consider the mass also, then it is the conservation of energy plus mass. That is the first law of thermodynamics. The main problem of first law is it cannot predict or cannot tell whether a particular transformation of energy will be spontaneous or not. Spontaneous or not means, suppose, sorry, if you rub your hands, you are doing some mechanical work. And that mechanical work will be spontaneously converts or it spontaneously will generate some amount of heat. It is a spontaneous process, mechanical work to heat. But the reverse, heat to mechanical work, or suppose you are burning some amount of coal, that is some chemical energy will be spontaneously converts into heat. It is a spontaneous process. But in order to use that heat to produce some mechanical work, heat to mechanical work, that is, here it is on the reverse side and here it is on the some other forms, one form of energy to other form of energy. This is not a spontaneous process. Mechanical energy, mechanical work to heat or chemical work to heat, in fact, any transformation which will produce heat, that is actually spontaneous in nature. But heat to any other form, that is not a spontaneous process. You have to do some amount of work. You have to introduce some amount of engine or machine in order to utilize the heat energy to perform some work. But first law cannot tell that. That is a particular form of conversion from one form of energy to other, whether it will be spontaneous or not, whether we require some other devices to transform that form of energy, first law cannot tell. It simply tells the interconversion of energy and the equivalency of the energy. So this is the domain of second law. Domain of second law, that is, whether a particular transformation of energy will be spontaneous or not, that is the domain of second law. For example, I was talking about any form of energy to heat that is spontaneous. That is actually, this is the another statement of second law. There are some other statements also, I will tell those. For any transformation for which randomness will increase, for any transformation of energy, if randomness increases, then that process will be spontaneous. Suppose you are doing some mechanical work, suppose this one, up and down of this piston, that is some mechanical work, or rotation of a paddle wheel, this is some form of mechanical work, or you are rubbing your hands, this is another form of mechanical work. In all cases, when heat will be produced, that heat will be, suppose in all cases heat are producing, but that heat, it will be spreaded all over on all the possible direction, it will be spreaded out. For a mechanical work will be happening at a particular direction. Here it has a particular direction. Here it has a particular direction. You are rubbing your hands, it is a particular direction. But when the heat will be produced, heat cannot be confined. It will be spreaded all over, all possible direction. As a result, when heat will be produced, your randomness will be increased. Randomness or disorderness, it will increase. Now, all these possible changes for which randomness or disorderness increases, that processes are called spontaneous process. But you can see, if you want to do or if you want to confine heat and do some mechanical work, that means you are decreasing the randomness, you are increasing the orderness. Decreasing randomness or increasing orderness, that is not a spontaneous process. To do that, we require to involve some other type of particular type of machine or engine. Otherwise, you cannot do it. That's why our atmosphere, it is a vast reserve of heat. You can see today normal temperature all over the India, mostly it is around 40 degrees centigrade. So you can see how much heat we have right now in our atmosphere. But we cannot simply use that heat to do some mechanical work. For that, we have to devise some kind of machine or engine. So apart from this, in terms of randomness or disorderness, that is relation between randomness and spontaneity, apart from this, there are some other conclusions which we'll get from the first law. I told you in case of first law, W reversible, that is equal to 0. Q reversible, that is equal to 0 for PV process. For a pressure volume process for the whole cycle, Q reversible, if the process is a reversible process, in fact, process is a reversible, process should be reversible. If it is a reversible process, Q will be equal to 0 or W will be equal to 0. And in numerical problem also I have shown you W expansion minus nRT ln V2 by V1 considering ideal gas. And W compression, it will be the same thing with positive sign, nRT ln V2 by V1. And W total, it will be equal to 0. This is the isothermal process. nRT ln V2 by V1, this expression are dealing with isothermal process. What is isothermal process? Isothermal process means temperature constant process. Temperature constant process, it can be in other way, it can be said as a single heat reservoir process. Single heat reservoir. A process which is occurring at a single heat reservoir. Single heat reservoir, that means it is a constant temperature process or isothermal process. Hence, in a cyclic single heat reservoir process, heat cannot be converted into work. No heat can be converted into work in a cyclic reversible isothermal process. And this is the statement, one of the statement of the second law. What is that statement? Exact definition of that statement. The statement tells there are actually two statements. One is Kelvin-Planck statement. This is saying it is impossible for a system working in a cycle and connected to a single heat reservoir. If a system which is working in a cycle and connected to a single heat reservoir to produce positive amount of work by absorbing equivalent amount of heat from that single thermal reservoir. In other way, in isothermal cyclic process, heat cannot be converted into work. In isothermal means single heat reservoir. in isothermal cyclic process, heat cannot be converted into work. The same thing, this is the Kelvin-Planck statement. It is impossible for a system working in a cycle and connected to a single heat reservoir to produce positive amount of work by absorbing equivalent amount of heat from that single heat reservoir. One can say, sir, why this word is required? Sorry, not single. Why the cyclic word is actually required? You see, cyclic is required because suppose you are expanding. You cannot expand anything to an infinitely large amount. Infinitely large amount you cannot expand. Then dimension of your engine or dimension of your system will be infinitely large. Now, any engine or any system should be of finite dimension. And whenever it will be finite dimension, the process will be cyclic or repetitive. That is, initially your expansion will happen, piston will go up to some particular point. Then again, there should be compression. The piston should come back to its initial state. Again, it will be expanded. In that way, continuous cyclic process should be there to become any system or engine of finite dimension. Anything cannot be infinitely large. That's why the process will be cyclic. Now, following this statement, in a cyclic reversible isothermal process, heat cannot be converted into work. That is the Kelvin-Planck statement. And also there is another statement, that is the Clausius statement. It is of our human experience. All these statements have come from our human experience. That is, it is impossible for heat to move by itself. By itself means without any other way of action, without any other action. It is impossible for heat to move by itself from a low temperature medium to a high temperature medium. That is, heat cannot be spontaneously go from a lower temperature body to a higher temperature body. Heat can spontaneously move from higher temperature body to lower temperature body. But the reverse, heat cannot move spontaneously from a low temperature body to high temperature body. So this is the Clausius statement. In fact, one can show the both statements are actually equivalent in nature. Okay, so now,
Sir, one doubt.
Tell.
Sir, the first statement was given that positive work cannot be done by absorbing equivalent amount of heat. So, sir, according to
In an
the
isothermal cyclic process, you are not
yes,
telling
sir.
the main point. In an isothermal cyclic process, cannot be converted into work.
Sir, but this can be proved by the first law itself because delta U is equals to W plus Q, and for cyclic reversible
I am
process,
not
delta
telling,
U is two.
see. In case of irreversible, if it is irreversible, the problem will be more problematic. Then W will be positive. You will not gain any work. Rather, surrounding has to do work in the whole cyclic process. It will be more complicated. That is I have explained to you in the previous day.
Yes,
Here
sir. Sir,
we are considering
reversible.
reversible process. In case of reversible process, you will not get any, W will be 0 for a reversible process. That is, heat cannot be converted in a cyclic reversible process. If it is irreversible process, then it will not be 0, rather W will be positive. That means you will not get any work, rather surrounding has to do work. Okay.
Yes, sir.
So that's why we are not considering the irreversible process here. It will be more complicated. Okay. So that means in your cyclic reversible process, heat cannot be converted into work. This is number one. And number two, if you want to move or if you want to transfer heat from a lower temperature region to higher temperature region, you have to do some work. Otherwise, you cannot transfer heat from a lower temperature body to higher temperature body. So these are the two statements, and based on the two statements, your second law has been devised. Okay. Now, how to convert heat into work? If in a single temperature reservoir, if in a single temperature reservoir, heat cannot be converted into work. That means you at least require two temperature regions. One will be at higher temperature, one will be at lower temperature. This is the source of heat. It is at higher temperature, it is the source of heat. It is at lower temperature, it is the sink of heat. And you can add or you can connect these two temperature reservoirs by a cyclic system or cyclic machine or cyclic engine. What will be the nature of the intermediate steps? The nature of the intermediate steps will be such that from this higher temperature source, the engine will absorb some amount of heat. It will utilize a part of that heat to do some work on the surrounding and will discard the rest amount of heat to the lower temperature sink, and again it will go back to its initial state. That means again the system will absorb some amount of heat from the higher temperature source. It will utilize a part of it to do some work on the surrounding and will discard the rest amount of heat to the lower temperature sink. A system can never utilize the all heat to do the work on the surrounding. Always there will be some loss of heat to this lower temperature sink. That is, if we calculate the efficiency of this whole engine, efficiency will be equal to the total work done divided by the amount of heat absorbed from the higher temperature source. That is W total by mod of Q. Here I am writing the mod sign because work done on the surrounding, that means it will be actually negative quantity, but heat absorbed, that will be actually positive quantity, but efficiency cannot be negative. In order to maintain that one, we are giving the mod sign, or you can give mod sign here, whatever it may be. Overall, I am taking the numerical value. That is, what is the total work done by the system divided by the total amount of heat absorbed from the higher temperature source. But a system cannot utilize all the heat absorbed from the higher temperature source. That is, efficiency can never be 100%. Efficiency of what? Efficiency of conversion of heat into work can never be 100%. Always there will be some loss of heat to the lower temperature sink. And depending on these intermediate steps, there may be different type of engines or different type of machines. And among those, the most primitive one was the ideal Carnot cycle. All other devices or engines which has been devised, like Otto cycle, diesel cycle, whatever it may be, the basic concept was taken from this ideal Carnot cycle. So in an ideal Carnot cycle, what are the intermediate steps? The there are actually total 4 intermediate steps. Just a moment, I have a call. Okay. The first step is the reversible isothermal expansion. And for simplicity, we are taking ideal gas as the working substance. It is not necessary to consider ideal gas as working substance, but if you consider, your numerical analysis will be much easier, and ultimate whatever conclusion we will get, that conclusion will be valid for all other systems. Ideal gas as the working substance. The first step is the reversible isothermal expansion of ideal gas. Second step, reversible adiabatic expansion of the ideal gas. Third step, reversible isothermal compression. Okay, am I audible now?
Yes,
Hello?
sir.
Okay. Fourth step will be the reversible adiabatic compression. So these are the total 4 steps in an ideal Carnot cycle. Now let us draw the PV diagram for this ideal Carnot cycle and changes of different parameters under each intermediate steps. This is P, this is P. So let this one initially it is the P1, V1 temperature T. This is P, point 2. The first step is the reversible isothermal expansion. Suppose isothermal expansion, that means temperature will remain the same. This is point B. Volume will be increased because it is expansion. Obviously, pressure has to be dropped because temperature remaining the same, pressure has to be dropped. Pressure will be decreased. And it will be like this. The variation will be like this. The second step is the reversible adiabatic expansion. For reversible expansion, temperature drops. And suppose it is the point C, temperature drops, that is T2 will be less than T1. Volume will be increased, V3 will be greater than V2. Pressure will also drop, P3 will be less than P2. And it will be like this because it will be more steeper. Adiabatic process, PV slope will be more steeper than your isothermal process, and it will be like this. Then compression. Isothermal reversible compression. Isothermal process, temperature will remain the same as T2. Volume will be decreased to V4. V4 will be less than V3. And pressure will be increased than your P3. And it will be like this. Last step, that is the adiabatic compression. But for adiabatic compression, temperature increases. And if you increase the temperature in such a way that it becomes or it goes to the initial temperature T1, That's T2, it is at lower temperature. T1, it is at higher temperature. T1 greater than T2. For adiabatic compression, temperature increases and temperature will be high, will move from T2 to T1. Automatically, pressure and volume, it will be reaching the initial state of P1 and P1. The system will go back to its initial state. So this is the intermediate steps. This is step 1, this is step 2, then step 3, step 4. And we are considering ideal gas as working substance. Now, as it is an isothermal process for ideal gas, there will be no change of internal energy for ideal gas. There will be no change of internal energy. And what will be about Q? Q, that will be nRT1 ln V2 by V1. What about W? W will be minus nRT1 ln V2 by V1. It is an expansion process, that's why W is negative. V2 is greater than V1, hence W will be negative. Q will be positive because this amount of heat the system is absorbing from the higher temperature source, and this is the amount of work done by the system on the surrounding, and there will be no change of internal energy. So this is for step 1. For step 2, which is an adiabatic process, here Q is equal to 0. There will be no heat change. And what about delta U, which is equal to W? It will be N into Cv bar, final temperature T2 minus initial temperature T1. N into Cv bar, T2 minus T1. And you can see T2 is less than T1, that's why it is a negative quantity. And W negative means it is an expansion process. N Cv bar T2 minus T. Similarly, for third step, now it is a compression. Again, it is an isothermal process for ideal gas. Whether it is expansion or compression, there will be no change of internal energy for an isothermal process for an ideal gas. And del U at constant temperature, that will be equal to 0. Again, what about Q? Q will be now, okay, W will be now, I am writing minus nRT2 ln. What is the final temperature volume? V4 by V3. And you can see V4, the volume is
V4.
decreased, V3 is high. That means it is a fraction, ln of a fraction, that is negative. There is a negative sign. Total, this is positive. Total, this is positive, that is compression process. Hence, here W is equal to minus nRT2 ln V4 by V3. It is actually a positive, that is compression process. And what about the corresponding Q? The same value with the positive sign, that is nRT2 ln V4 by V3. And you can see it is a negative quantity. That means this amount of heat will be released to the surrounding. So these are the different parameters for this step. For last step, again, WQ is equal to 0 and W will be equal to N into Cv bar, final temperature T1 minus T2. T1 is greater than T2, hence it is a positive value. That means again it is an T1 is greater than T2, that means it is a positive value, that is compression process. So these are the different parameters for the 4 intermediate steps. Now, if we write what is the W total for the whole cycle, You can see here W for step 2, NCV bar T2 minus T1, and here NCV bar T1 minus T2. So if I sum these two, this will cancel because it is T2 minus T1, it is T1 minus T2. These two will cancel. So only there are two terms, this term and this term. So let us write. So it will be minus nRT1 ln V2 by V1 minus nRT2 ln V4 by V3. Now if we write V4 by V3 in terms of V3 by V4, then it will be minus nRT1 ln V2 by V1. Now it will be positive sign nRT2 ln V3 by V4. Now, these are two adiabatic process, adiabatic step, and we have considered ideal gas. So, what is the relation between temperature and volume for these two steps, in these two steps?
So TV to the power gamma minus 1.
T1 into V2 to the power gamma minus 1, because here temperature T1, volume V2. Here temperature T2, T2 into V3 to the power gamma minus 1. And for here, it is temperature T1, V1 to the power gamma minus 1, that is equal to T2 and V4. T2, V4 to the power gamma minus 1. If you divide these two, this expression and this expression, if you divide it, what you will get? That is V2 by V1. It will be equal to V3 by V4. Thus, in place of V3 by V4, we can write nRT1 ln V2 by V1 plus nRT2 ln V2 by V1. In place of V3 by V4, we can write V2 by V1. Now, if we take nR ln V2 by V1 common, then, and minus also if you take common, then it will be T1 minus T2, this T2, then nR ln V2 by V2. That is minus n into R, T1 minus T2 ln V2 by V1. This is the W total. Then what is the efficiency? That is the total work done by the system. Efficiency of the engine, eta. The efficiency is the W total divided by maximum possible work, maximum possible work available if all the heat absorbed from higher temperature source be fully converted into what? This is the total statement. That is the total work for the cycle which are actually we are getting divided by maximum possible work that would be available if all the heat absorbed from the higher temperature source be fully converted into work. So what is the amount of heat the system is absorbing from the higher temperature source? This one. And if this amount of heat be fully converted into work, then what is the maximum possible work? That is this one. This is the maximum possible work. Hence, efficiency will be the maximum possible work means A0 T1 ln V2 by V1. And what is the actually W total for the whole cycle? Okay, minus A. Minus A0 T1 minus T2 ln V2 by V1. Hence it will be T1 minus T2 by V2. Or you can write W is equal to W total by Q. The same thing. W total, that is, if you take the mod of it, then it will be NR T1 minus T2 ln V2 by V1, and Q1 actually, it will be Q1, that is the maximum possible heat absorbed from the higher temperature source, that is equal to NR T1 ln V2 by V1. Ultimately, same expression, T1 minus T2 by T1, that is you are getting as the efficiency of this ideal Carnot cycle, where T1 is the temperature of the source and T2 is the temperature of the sink, or that is the delta T by T1, which is equal to 1 minus T2 by T1. 1 minus T2 by T1. In any of this expression, you can mention the efficiency of the Carnot cycle. Now, from this expression of the efficiency, that is how much heat has been converted into work. Efficiency means how much heat has been converted into work. We can derive certain conclusions. What are those conclusions? See, all the steps we have assumed as a reversible step. If any of the intermediate steps becomes irreversible, efficiency will drop, efficiency will decrease. That is, reversible Carnot cycle provides maximum possible efficiency. Efficiency in converting heat into work. If any of the intermediate steps becomes irreversible, efficiency will drop. That is, less amount of heat will be converted into work. That is number one. Number two, as T1 is higher than T2, your efficiency is always less than 100%. That is, your efficiency cannot be, that is, heat cannot be converted into work by 100%. Always there will be some loss of heat to the lower temperature sink. Heat cannot be converted into work with 100% efficiency. Always during the process of conversion of heat into work, there will be some loss of heat to the lower temperature sink. Efficiency will be always less than 100%. If T1 is equal to T2, efficiency will be 0. Efficiency will be 0 means no heat will be converted into work. T1 equal to T2, that means now there are not two temperature regions. There is only one temperature region. One temperature region means isothermal cyclic process. No heat will be converted into work in an isothermal cyclic process. Then T2 cannot be 0 Kelvin. This is the conclusion from third law of thermodynamics. At T2 cannot be. If T2 cannot be 0 Kelvin, efficiency will be always less than 100%. This efficiency will be less than 1. In terms of numerical value, it will be less than 1. In terms of percentage, it is less than 100%. And temperature of any system in the universe cannot attain 0 Kelvin value. That is one of the conclusion of third law of thermodynamics. Then another, efficiency can be increased either by increasing T1 or decreasing the value of T2. That is increasing the temperature gap between the source and the sink. You can increase the gap between temperature of the source and sink by either increasing the temperature of the source or by decreasing the temperature of the sink. Between these two, the second process is more efficient. It is more efficient because by definition it is T1 minus T2 by T1. That's why when you are increasing the T1, you are increasing delta T. There is no doubt. But also you are increasing this T1 also. That's why efficiency can be increased by two ways, either by increasing the temperature of the source or by decreasing the temperature of the sink. But among these two processes, the second step, that is decreasing the temperature of the sink, is more efficient. One can show it by mathematically also. By taking some derivative, one can also show it. Number last 5. We have taken the ideal gas as the working substance, but ultimately whatever efficiency expression we have got, it depends only on the temperature of the source and temperature of the sink. It does not require the characteristics of the working substances. Hence, for the whole process, if we do or if we use, suppose your Van der Waals gas as the working substance, you will get the same expression of efficiency. That is, the efficiency of ideal Carnot cycle is independent of the working substance. Then, from the ideal Carnot cycle, we get the concept of an another state function, which is the entropy function. How?
Sir.
Yes.
Sir, we have another class, sir.
From when?
So from 12.
Okay, I am stopping. From the ideal Carnot cycle, we get the concept of another function which is called entropy function. Another thermodynamic state function which is called entropy function. Next, I will show you how we will get that concept. But due to all the conclusions which we are getting, all these conclusions are very effective in devising different types of heat engines. That is, those engines or systems which are utilized to convert heat into work. That's why ideal Carnot cycle is called the basic thermodynamic cycle. And different thermodynamic equations or different thermodynamic relations can be derived from the concept of this ideal Carnot cycle. That's why it is called the basic thermodynamic cycle. So today I am stopping here. Next day again I will show you how from that ideal Carnot cycle one gets the idea of this entropy function. Then we will discuss what are the properties of that entropy function and so on. With this I am stopping. You go through all the notes.